So today is December 1st and you're here for Econ 249. You're looking at a sign that talks about evaluating your courses. So I got an email saying that the course evaluation link is open. So once you click on this link and you log in, you will see a list of all your registered courses. When you select Econ 249, this course, and you submit your course evaluation, once you submit, the next page will give you an option whether to inform your instructor. And once you check yes, I will automatically get an email saying that student so-and-so has submitted their course evaluation. And I've decided to give 1 point towards extra credit if you submit your course evaluation. Okay, so not all instructors are doing that. I've decided to do that, and as you can see here, the due date is December 14th. Rad, you said you completed it last night and sent proof. Yes, I've got a few emails already with students who have already submitted it. And the other question, Diana, is until when will they be up? Well, it's due December 14th, so I assume the link will be open till December 14th. Okay, so this is where you would go to qc.cuny.edu/evaluate. Any questions for me before we start class today? So your final exam stays the same. It's December 17th. That's the date given to us on CUNY First. And when we get closer to that date, I will send you information about the exact chapters, how long the test will be, and all that stuff. Okay, so we are going to continue with chapter 12, which was about testing hypotheses. And if you recall, in the last class, we completed a z-test for the population mean when the population standard deviation was known, sigma was known. And we did both. We did a one-tail as well as a two-tail test. Okay, and this is what we did in the last class, this example where we checked to see if the average lifespan has changed, and that was considered a two-tail test. And then we also checked to see if the average lifespan has increased, and that was considered a one-tail test. So in today's class, what I'm going to do is we're going to perform a t-test for the population mean when the population standard deviation sigma is unknown. Okay, so it's basically the same 7 steps, but now it's a t-test. And that's how the remaining topics will be covered in this chapter. So this is the last chapter for this course. Okay, so I'm going to immediately start with an example, because that way you can see how we get through this hypothesis test. So this is the example. A certain type of rockets have a range of at least 5,000 meters. We believe that the range will be different after storage for some time. 5 of these rockets are stored and then tested. The ranges found in the tests are as follows, and it's given in meters. So let me backtrack a little before I read the rest. We're told that we're looking at rockets. And we're also told that these rockets have a range of traveling at least 5,000 meters. So 5,000 meters is the minimum, or more than 5,000 meters. But now we think that after storing these rockets, something's going to change. So 5 of the rockets are stored, and then those 5 are tested. So they test the range for those 5 rockets. And these are the ranges they found: 4,980 meters, 5,200 meters, 4,720 meters, 4,820 meters, and 4,800 meters. So they've tested it. The sample kind of looks like it's less than 5,000 meters, but we can't make a decision based on that. We have to complete a 7-step hypothesis test. So part 1 of this question says, has the range changed Part A says, has the range changed? It's only asking if it's different from 5,000 meters. Part B says, does the range appear to be reduced after storage? And use alpha of 0.01. So a couple of things I'm going to ask first. How do you know you're doing a hypothesis test for population mean and not proportion? So I know it says on the slide, but what is it about this example that indicates it's not proportion? I think that's a better way of asking the question. What is not given in the slide? Through process of elimination, how do you know this is population mean? Rad, you say standard deviation is not given. So that's not answering the question I'm actually asking. I'm asking, how do you know mean and not proportion? So there's nowhere in the question that has the word proportion. It doesn't have the word percent. Okay, it's giving me an exact value of 5,000 meters. That 5,000 meters has nothing to do with percent or proportion. So through the process of elimination, I'm going to say that we're testing for population mean, the average range for these rockets. Okay, so I'm not dealing with proportion. That's the first thing. The next thing is, how do I know Z table or T table? Or in other words, Z test or T test? So now, Red, how can you answer that?
I guess because the standard deviation we need for the z-test.
Right, so that would be the answer for that question. Because population standard deviation is not given in this question, so there's nowhere that says standard deviation to do with the population, we don't know what it is. So we have to use the t-table, or now we're going to use a t-test. Okay, so these things are understood. Okay, I'm going to go to the next slide, which is starting our 7 steps for a hypothesis. Okay, so I'm going to write down step 1. Step 1 is to state your null hypothesis. So the null hypothesis, HO, states that, now we decided mean, so that means population mean, mu, is greater than or equal to. Now why greater than or equal to? Well, the question said that currently we think that the rockets have a range of at least, yep, Kevin, you're right, at least 5,000 meters. So at least means greater than or equal to. The minimum is 5,000. It has to be 5,000 and more than 5,000, at least. And remember, there's always an equal sign in step 1. There's an equality with the null hypothesis. So it's greater than or equal to. And then I can also say that this is the initial expected population mean, mu 0. So that's the 5,000 meters. Step 2 is to state my alternative hypothesis, H1. H1 states that mu, the population mean, now I have to do the exact opposite of step 1. So the opposite of greater than or equal to is less than. It's never going to have an equality. So mu is less than 5,000 meters. What I forgot to mention is we're going to do only part B of the question. So let me actually type it up on the top here. Part B of the question says, does the range appear to be reduced after storage? So we're not doing part A. Part A asked, has the range changed? We're doing part B. So that's why I have less than, because it said, does it appear to be reduced after storage? Now, this is where I have to indicate whether it's a one-tail or two-tail test. So what should I indicate here? Is this a one-tail or two-tail test? If there is a do not equal sign in step 2, the alternative hypothesis, then it's a two-tail test. But since this sign is less than, this is going to be a one-tail test. If the sign was greater than, like let's say the question said, does the range appear to have increased after storage? That means greater than. I'm testing if it's greater than 5,000 meters. That would also be one tail. Any questions for me? No. Okay. Then step 3 is to state your level of significance, alpha. And in the question, you were given alpha is 0.01. Now, should I divide alpha by 2? Okay, you're right. Armila, Danielle, Rad. Because it's a one tail, I do not divide alpha by 2. So I leave it as it is. I don't know why this has a 1 and a 2 here. This shouldn't be there. But this is step 4. Step 4 is my test statistic. Now, in the previous class, we calculated Z observed as a test statistic. Now we're doing T observed because we don't know the population standard deviation. So this is the formula. And the formula is pretty much the same, except you divide the denominator. The denominator is S, which stands for sample standard deviation, rather than sigma, which would have been population standard deviation. So let me give you a few things that were given in the question because you don't have it in front of you. So they took a sample of 5 rockets, so N was 5, and they found that the individual ranges for the 5 rockets was 4980 meters, 5200 meters, 4720 meters, 4820 meters, and 4800 meters. So this is what was given in the question. So from here, I can figure out that N is 5. So that means that's my square root of N. X bar, I have to calculate from the 5 observations in my sample. So I can calculate X bar to be the sum of 4980 plus 5200, all that divided by 5. So Colette, did you get the same value as Rad? Okay, yep, same thing. All right, so then we can say that the sample mean is 4904. Okay. Now the next thing is sample standard deviation, S. So S, I'll write the formula for you, and then you can either use Excel or you can use your, so that's sigma sum, or you can use your scientific calculator and get the standard deviation. So if you're doing it manually, it's the sum, sigma, the sum of x minus x bar squared divided by n minus 1 and the whole thing square root. So I'll give you a moment, and if I can have Anita, can you give us that answer? And Hiba, if you can confirm what Anisa has. So if you put all these values in Excel and you select standard deviation on that icon where the sum and the average is, you should be able to get the answer. Anissa or Heba, are you close with the answer?
Professor, is the X bar the 5,000 or the 4904?
X bar is 4904. So if you were doing this manually, you would take the first value, which is 4980, minus the sample mean, which is 4904, square it, plus take the second observation, 5200, minus the sample mean, 4904, get that answer, square it, plus keep going with the third, fourth, and fifth observation, divide everything by n minus 1, and then square root. If you put the 5 values in Excel and you ask Excel to do STDEV, which is standard deviation, you should get your answer. Okay, we have 2 with the same answer. So I just want to make sure you know how to do this, because this is really testing you on topics from the beginning of the semester. So get really comfortable with calculating mean, standard deviation. Don't spend time trying to figure it out during the test. Even if you're working with someone else at the same time when you do the test, you're going to have different numbers. So you'll have different answers. So make sure you understand the method. What's easier for you? Is it easier on the calculator? Is it easier on Excel? Do you need to put it on an Excel spreadsheet and have columns? So get used to calculating this. Not all information is automatically given to you, right? Okay, so let's go with 190.473. Okay, so that's the value I'm going to put in the denominator here. And then can I have Hirak? Can you give us the answer for test statistic? Anyone have an answer? Okay, so let's go with what we have here, negative 1.13. So I'm going to use 2 decimal places here. When you're doing your homework, make sure you read the question carefully if they're asking 2-place or 3-place decimals. Okay, so this is our T observed value. T observed value. Step 5 is the critical region. Critical region means you're going to draw the graph and indicate which area of that graph is the rejection region and not the rejection region. Okay, so I'm going to do first the rejection method. So I'll put down here number 1. So this is the rejection method. Okay, so for me to do that, I have to draw the graph, and then I have to look at step 2 to decide whether this is a one-tail or two-tail test. So since this is one tail, I have to decide now if I shade to the left or to the right. What do you think I should do? Karina, you say left. Why? Because it's less than. Because this sign says less than. Yep. So I'm going to shade only to the left. And the point here indicates my critical value. So my critical value, now it's got to be either Z or T, but since we decided we're doing a T test, this is going to be negative T. How do I know negative? Because it's on the left side. That's all it is. And remember, the subscript is T at n minus 1, comma, alpha. Usually alpha divided by 2, but since this is a one-tail test, it's just comma alpha. So negative T subscript n minus 1 comma alpha. That's my critical value. Okay, now I am told that alpha is 0.01. So I can indicate that on my graph here. This shaded area is alpha, which is 0.01. That was given in the question. Okay, so I'm going to use this information to look up on my T table to get the critical value. Okay, so when I go to my T table, I have to first decide on what degrees of freedom to go down that first column. So what's my degrees of freedom? 4. Arzu, you're right. So remember, it's just a fancy name for n minus 1. And since n is 5, my degrees of freedom is 4, comma, alpha is 0.01. Okay, so I'm just rewriting that here. Then I can do one more step here. So I'll show you the normal distribution tables in a moment, but just to let you know, you're going down to 4 degrees of freedom. Go across to one tail probability. At one tail probability, select the value of 0.01. So go down 4 degrees of freedom, go across to one tail probability when alpha is 0.01. The T value that you're going to see on the table is, oh no. Okay, I clicked the wrong thing, sorry. But the T value is going to be 3.747. Okay, this was negative 1.13. This was 5,000. So again, the table is not going to give you the negative value, but we know that it's negative because it was on the left side. Okay, I will show you the normal distribution table in a moment, but let me just quickly draw this. So this is the side we shaded. This was our T observed value. So I'm going to write, not T observed, sorry, critical value. T at, so negative T at n minus 1 alpha. And according to the table, we got that as negative 3.747. Okay, any questions for me? Okay, so still on this graph, we have to indicate the rejection region. So the shaded area is where I decide to reject the null hypothesis. The unshaded area, so anything to the right of my critical value, is where I do not reject the null hypothesis. So now, since we're doing the rejection method, so number one was this method is the rejection method. I have to look at where T observed falls on this graph. So if this blue point on the graph is my critical value, and that's negative 3.747, it's going to fall to the right of that critical value. So that would be my T observed value, and that would be equal to negative 1.13. So what do you think the decision is? Yes, Jeffrey, Armila, you're right. Do not reject the null hypothesis. So this decision is do not reject the null hypothesis. So this is 1, 2, 3, 4, 5, 6. So we're on step 6. Step 7 is the conclusion. I'm going to come back to the conclusion after I do the second method, which is the p-value method. Okay, so we're going to do that next, the p-value method. But before I do the p-value method, I want to go to the normal distribution tables and show you how I got my critical value of negative 3.747. Okay, now remember, before we leave here, you need to understand the reason why we decided to not reject the null hypothesis is because the T observed value is greater than the critical value. So it ended up falling on the unshaded region, which we do not reject the null hypothesis. If my T observed calculated value came out to be negative 5, then it would fall in the shaded area and I would reject the null hypothesis. Okay, so now any questions before I switch, because I won't be able to get this again? Okay, so here's the normal distribution tables, and you would go to the last page, the third page with the T tables, and let's make this a little bigger. So we're told that we took 5 rockets in our sample, so the degrees of freedom would be n-1, that was 4. And then we were interested in a one-tail probability. So I went across here to one tail and I looked for alpha of 0.01. So that gives me a T critical value of 3.747. I know it's negative because the tail is on the left, so I put a negative 3.747 sign. Any questions for me? Yeah, Red, go ahead.
Professor, I forgot how to check this on Excel. I did t.dist, and it's asking for x value, degrees of freedom, and if it's cumulative. What's the x value?
I think you're doing it for confidence. I think it's T inverse, I think.
Oh, it's T inverse, okay.
Yeah, T.inv. Thank you, Angel.
Oh, okay, got it. Okay, thank you.
Yeah. Okay, so now the same thing. Let's see if we get do not reject using the p-value method. So actually with the p-value method, I'm going to need this table as well, but let's set it up and then come back here. Okay, so going back to our slide. Okay, so I'm going to the next slide. Let's make this smaller again. So the next slide actually gives the answers. So we did step 1, that stays the same. The null hypothesis. Number 2 is the alternative hypothesis. Number 3 is the level of significance. 4 is your test statistic. That stays the same because it's a calculated value, t observed. Step 5 is your critical region. Now your critical value also stays the same because that's t at n-1 alpha. In the rejection method, you found that your decision was to do not reject the null hypothesis. Now we're going to do method 2 to check using p-value. Okay, with p-value and a t-test, this is what you would do. At 4 degrees of freedom, so first you have to consider your degrees of freedom. So go down to your table to 4 degrees of freedom. And then go across looking for the value that is closest to your t observed value. So your t observed value is negative 1.13. Now there's not going to be a negative, so let's use it as the absolute value, so 1.13. So when you go to your degrees of freedom, go across and look for 1.13. You're not going to see the exact value, but get to the closest value that is to 1.13, whatever number is closest to that. And then go up to figure out what the p-value is. So go up to the top of the table and make sure you're at one tail, because we're dealing with one tail, and see what that p-value is. So I'm going to put down here that the p-value, and I'll show you on the table, but the p-value comes out to be 0.10. Okay, so now remember the condition here. Your condition is always reject the null hypothesis if your p-value is less than alpha. In the question, you were given alpha is 0.01. Now, p-value is 0.10. So, is it greater than or less than alpha? So, is p-value greater than or less than alpha? Dongyan, you say greater than, everyone says greater than, so it is greater than alpha. Okay, so since the p-value is greater than alpha, then the decision is going to be what? What's the decision? So my condition is reject the null hypothesis if p-value is less than alpha. Danielle, you said do not reject the null hypothesis. Agreed. So do not reject the null hypothesis. So this method is the p-value method, and we got the same decision as the rejection method. Okay, so make sure you understand how to do this. If this was a two-tail test and I was doing the p-value method, when I go up to find my p-value, I would read it along the two-tail test. Again, I'll show you that on the table in a moment. But we're not done. The last step is the conclusion. And whenever your decision is do not reject the null hypothesis, do not reject the null hypothesis, you have to start your sentence with this: there is not enough evidence to prove that. Why? Okay, well, let's see. If I decide do not reject the null hypothesis, I'm saying This is okay. I don't have to reject it. The range of the rockets is at least 5,000 meters. I couldn't prove that it's less than 5,000 meters. I couldn't prove that after storing it, the range has reduced. So it's still correct. The null hypothesis is still okay. So my conclusion will always start like this when my decision is do not reject the null hypothesis. There is not enough evidence to prove that storage has reduced the average range of these rockets. There's not enough evidence to prove my alternative hypothesis. There's not enough evidence to prove that the person is innocent. So just because the person is not guilty doesn't mean the person is innocent. Okay? So in the same way here, not enough evidence to prove that it has reduced. So that's always the sentence you would start with for conclusion when your decision is do not reject. Questions for me? Okay, so let's go back to the normal distribution tables, the third page, the t-table, to figure out how to find the p-value. Okay, so going to the third page, let's make this bigger. Now, I said that the t observed value that you calculated was equal to negative 1.13. Okay, so the first step is go down to your degrees of freedom, and that was 4. And in this row, I'm going to look for 1.13. Now, I don't see 1.13, but this is the closest value to 1.13. Now I'm going to go up, and since we're working with a one-tail probability, this is my p-value. Questions? So that's how we found p-value to be 0.10. So this is how you would find p-value when you're working with a t-test. If I was dealing with a two-tail probability, p-value would have been 0.20. Okay. So this is how you do a hypothesis test when you're not given the population standard deviation and you're doing a t-test. A couple of things I want to mention. Okay, so we finished this slide, making it smaller now. The next slide gives you a summary of how to figure out whether you're doing a one-tail or two-tail test. So with a two-tail test, your alternative hypothesis, H1, will always have a not equal to sign here. The right side, right tail is shaded when this is greater than, that's a one-tail test. And on the left side, when you have less than, you have you shade to the left, one tail. Okay, so it's a good slide to remember. Next thing I want to bring up is this topic of ethical issues. Now you have learned hypothesis testing, and we're using this method called inferential statistics, where you take your sample result and infer or make a conclusion about the population. So you're basically doing empirical methods with hypothesis testing using inferential statistics. So it's a great method that uses a standard formula and a standard set of analysis. So that means the researcher can be completely objective, right? Because it's a standard. We're not using my method versus your method. It's a very objective standard set of analysis. But I can also argue that it is based on some value judgment. So when you're reading an article or you watch the news, always ask questions. Distinguish between poor research methods and unethical behavior. So how could it be unethical when you're using a standard formula, standard analysis? Okay, I'll give you some examples. So I'm saying that hypothesis testing, this process can be manipulative. How? Well, first, with the collection method. How did they collect the sample? Was it really unbiased without any measurement error? Was it a simple random sample? Would it have been better if you used a cluster sample? That's one thing. The second thing is the type of test. Well, did they purposely have a smaller sample? Did they not use the population standard deviation so that they could purposely use a t-test when they should have used the z-test and thereby getting a different t observed value compared to a z observed value? So that could be manipulating the results. The choice of alpha. If alpha was 0.01 versus 0.05, would it have given different decisions? The next thing is data snooping. Well, data snooping is looking for certain observations that's going to give you certain results. So if you use the p-value, then did you decide to do a one-tail versus a two-tail? So for example, in our answer with the rockets, we said that t observed was negative 1.13. Well, what if my t observed value was a positive value, like positive 4.33? What if? Well, still, it's do not reject the null hypothesis because we only shaded a left side tail. But what if I said I wanted a two-tail test and now I shaded two tails? Well, if my t observed value is positive 4.33, it could fall in the rejection region, and that changes my decision into rejecting the null hypothesis, which changes my conclusion. So that's purposely manipulating the data. That process is incorrect and it's unethical. Another method is cleansing of data. Once you have collected the data, now you're removing the values that are going to affect your conclusion. Unethical. And then finally, reports could be biased. The way the report is written is biased. You don't want to lead the reader to believe something until you come up with your conclusion and you state your conclusion at the end. So these are unethical methods of a research design that exist and you should be aware of. And answering the question in the chat, Karina, you say, can manipulating data give a bias or untruthful answer? Absolutely, right? Yeah, so this means bias. This means you are giving a false conclusion. The next thing I want to discuss today is putting it all together. So I know we have one more topic with hypothesis testing, and that has to do with proportion, and I will do that in the next class. But the next topic I want to do today is combining confidence intervals and hypothesis testing. Because initially when I started hypothesis testing, I said that it's another phase of inferential statistics, another phase of inference. Estimation was one, and estimation was confidence intervals, and hypothesis testing is the other. So both methods are coming up with an inference about the population. So what if we do an example where we put them both together? So the example is this. If you have the slides, when you pull them down from my stat lab, this slide that you're looking at is towards the end. Okay, so let me give you the background on this question first. We're applying confidence intervals and hypothesis testing. Okay, so let's say there's this organization that says that college students should have 7 hours of sleep. Okay, I don't know what organization, but let's say there's this institution that makes this claim that college students should have an average of 7 hours of sleep. So you decide to test that, and you take a survey of 25 students and you ask them this question: how much sleep did you get last night? Okay, and so your plan is you want to find out, is the average amount of sleep, it said less than, right? So let's change this. Not 7 hours. Okay, I'm going to purposely do it differently so that we practice both. Is the mean amount of sleep not 7 hours? And you want to be 95% confident of your answer. Okay. So we're going to do a confidence interval and we're going to do a hypothesis test to check whether if we're getting the same answer with both methods. So you ask these 25 students and they tell you how many hours of sleep. So you do a histogram here that you see on the right. Now, did you meet the randomization condition? Well, yes, the students were randomly selected and their answers were independent. So one student's answer did not affect the other student's answer. Are your values normally distributed? Well, if you draw your histogram, you can see that it's sort of unimodal and symmetric. So we can assume that you're dealing with a normal distribution. Now, you've never done this test before, so you don't know what the population standard deviation is. So that means you're going to do a t-test and use the t-table. Okay, so first let's start with our hypothesis test because we just did that. So it's a little easier. So I'm going to open a blank slide here. Any questions before I start? Okay, so here's my blank screen. Step 1 is for me to write my null hypothesis. So the null hypothesis, HO, states that the average amount of sleep is equal to 7 hours. So this is currently the situation. Step 2 says that the alternative hypothesis, H1 or HA, like in your homework and your textbook, is not 7 hours. So we decided to test this. We think that it's different. It's not 7 hours. Step 3 is my alpha value. Now you were initially told that you have to be 95% confident. So what do you think alpha is? Yep, exactly. Alpha is equal to 0.05. So in step 2, what did I not write? How many tails? Okay, so Yu Jiang, Arzu, you say we're dealing with a two-tail test. So if this is a two-tail test, that means I have to divide alpha by 2. So now alpha is equal to what? Oscar says 0.025. Okay. So even when you're doing your homework for chapter 12, make sure you do these 7 steps. It's just so much easier rather than jumping ahead and trying to answer the questions directly. The next thing is to figure out the test statistic. Are we dealing with Z or T? Is it Z observed or T observed? So Armila, we don't know what the population standard deviation is, right? So for that reason, it's going to be T. So T observed. Now here's the formula for T observed. Square root of N times X bar minus mu 0 divided by S. So I'll give you these values because you don't see it. But let's say when you ask those 25 students how many hours of sleep, you got the 25 values and you calculated, so N is 25, you calculated sample mean to be 6.64 hours, and you calculated sample standard deviation to be 0.215. No, sorry, 1.075. So these are the values that you had. So you can plug everything in and get the test statistics. So tell me what you get. What is mu 0? Yep, Dongyan, that's 7, and S is 1.075. So what's the test statistic value? Okay, Rad, you say negative 1.67. Anyone else? Okay, same thing. Okay, so negative. Step 5 is to draw my critical region. So critical region. So I'm going to draw it first, and I'm going to do only one method now. I'll do the rejection method. So here I am drawing my graph. I know it's two-tail, so I'm going to shade the tails. The tails together is alpha divided by 2 and alpha divided by 2. These 2 points are my critical values, the negative t and the positive t. So I have to look up on my table and look up 24 degrees of freedom with an alpha divided by 2 value. So this is, I'll just write alpha divided by 2. So I go down to 24 degrees of freedom, go across to two-tail test for the entire alpha value. So remember the entire alpha value. So I'll show you that in a moment, but remember, go down 24 degrees of freedom, two-tail alpha value, combined value of 0.05, which is 2.064. Okay, let me double check that. 24 alpha is 0.05. Yes. So this is my negative, and positive would be the same thing. Okay, so now if it falls in the shaded region on either side, that's when I would reject my null hypothesis. So same thing on both sides, right? Reject the null hypothesis. The unshaded region in the center is where I do not reject the null hypothesis. So now I look at my test statistic, my t observed value, and try to figure out where does it fall. Well, it seems to fall, if this is -2 and this is +2, then it's going to fall here. So that's my t observed value of -1.67. So now I can make my decision, which is step 6. And the decision is, what's my decision? Do not reject the null hypothesis. correct. Make sure you understand why you do not reject. It's because the t observed value is greater than the critical value, and it falls in the unshaded region, which is the do not reject region. So that's what our decision is, do not reject. And then step 7 is the conclusion. So how would I start my sentence? There is not enough evidence to prove that. And now let me go back to my actual question here. We decided we do not reject the null hypothesis. So that means we're saying this is okay. We're not rejecting this. So the average number of hours of sleep is 7 hours of sleep. I'm not rejecting that. So there's not enough evidence to prove that the average hours of sleep is not 7. Not enough evidence to prove that the average amount of sleep is not 7 hours. I couldn't prove my alternative hypothesis because I didn't have enough evidence to prove it. Any questions about this? So this is my hypothesis test. And the decision was do not reject the null hypothesis. I'm going to do the same thing now, but now I'm going to do my confidence interval. And how is that giving me the same answer? Okay, so same thing. You ask those 25 students, and you got all their hours of sleep, and that was your sample data. Now you're going to make a statement saying all students have an average amount of sleep as this range with a lower limit and an upper limit. So remember the formula for confidence intervals. This is previous chapter, x bar plus or minus. Now remember we're doing t, not z, for the same reason, because we don't know the population standard deviation. So t subscript n minus 1, it's a minus, comma, alpha divided by 2. Okay, so let me make that comma, alpha divided by 2. All that was a subscript. Now times s over square root of n. So that's the confidence interval formula. Okay, so x bar is the same thing here, sample mean. So that's 6.64 plus or minus. Now same way you would look up the t table. You go down to 24 degrees of freedom and go across to 2 tail alpha 0.05. So we said that t is 2.064. The whole thing times s is your sample standard deviation, which is 1.075 divided by your square root of 25. Okay, so now I need Katarzyna, can you give me the upper limit? And Jazib, can you give me the lower limit? So the upper limit is going to be 6.64 plus 2.064 times all this. The lower limit will be 6.64 minus 2.064 times all that. Okay, so this is less than mu. Do we have answers? Upper limit, I think what you have is just the margin of error. So add that to 6.64, and let's see if you get the same thing as what RAD has. Okay, so upper limit, Diana, you got the same thing. 7.15. So remember, this is hours, right? HRS. That's the upper limit. And then the lower limit, anyone have the lower limit? 6.2, 6.196. Okay, so let's go with that, 6.196. Okay, so now this is telling me I am 95% confident that the average amount of sleep that students in my class get between 6.196 hours and 7.15 hours. This is what all students get, between 6.19 and 7.05, so 7.15. Is 7 hours included in this interval? Oscar says yes. Yes, so 7 hours is included in this interval. So now it's giving me the same answer as my hypothesis test, because my hypothesis test is saying that I'm not rejecting the null hypothesis because that's correct. Mu is equal to 7. Okay, so I'm getting the same answer. It is equal to 7, and 7 is also included in this interval. So that means whenever your hypothesis test has a decision of do not reject the null hypothesis, you are not going to have a 0 included in the interval, in your confidence interval. Okay, because it's saying that this unshaded region is do not reject. So you're not going to have a 0 within this interval. So let me actually type that in here. When hypothesis test is do not reject, then 0 is not included in confidence interval. Any questions for me? So Rad, you say when solving this in Excel, are we inputting 0.05 as alpha or 0.025 as alpha? I believe it's 0.025 because you have to indicate two-tail, right? So if your decision is reject the null hypothesis, then you will come up with a confidence interval that does include 0. So that means you have the same answer for both. And in the next class, I'll explain a little bit more about what that means. Okay, so we're going to stop here. Any questions for me? I'm going to stop recording.